In the previous video, we went through and calculated the energy that it took to break up all the bonds on this side, on the reactant side, and then we also calculated the amount of energy released from forming the bonds, and when we did, we got a value of 12,444 kilojoules. So I want to talk a little bit about what that means and how we can incorporate that into the equation. So this is the amount of heat that would be released. When this is a positive number, it means the following, that it has taken more energy to break the bonds than was released when the bonds were formed. So that's a reaction that takes in energy. So we call that kind of reaction, and we've used this word before, so that is called an endothermic reaction. Okay, so there's two different symbols that we will use for heat, and there's a difference between them, but for the moment I'm just going to refer to this as delta H, and later I'll explain the difference in delta H and Q. So we say delta H is 1,244 kilojoules released, or sorry, absorbed in the reaction. So if we wanted to include that in the balanced equation, what we would have to do, I didn't leave myself enough room, but I'll put a plus, and we'd have 1244 kilojoules. So that's another part of the balanced equation. And we can use that information just like we use anything else in the balanced equation. So for example, if you were told that you only had 1 mole of CO2 and plenty of water, and you wanted to know how much heat would be, or how much energy would be absorbed in this reaction, well, since with 2 moles it takes 1,244 kilojoules, if it was just 1 mole of CO2 it would take half that. Okay, so that would be 622 kilojoules. So we'll look a little bit more later about how this is part of the stoichiometry. But for the moment, I want to emphasize 2 points. One is that when delta H is positive, the reaction is endothermic. That means it is absorbing energy. It means that the energy that it takes to break the bonds is greater than the energy that is released when you form the bonds. And then if we're putting this into the balanced equation, we would put it on the left side as part of the reactants. In this part of the video, I want to show you a kind of standard way of representing reactions. So we can do this on a graph that's called the reaction coordinate graph. And what we have across the bottom is just the reaction. So this is just sort of how the reaction takes place over time. And on the vertical axis, we have energy, which in this case would be kilojoules. Okay, so if we just arbitrarily just pick a point and start out here, this would represent, in this case, the energy of the reactants. And reactions go through what is called the activation stage. So this is the energy that it takes in order for the reaction to take place. So it's very common that we have to do something to get the reaction to take place. So this distance from here to here is referred to as the activation energy. But what we're actually interested in at the moment is the difference between the reactants over here and the products over here. So that energy difference is represented here, and that amount for this particular reaction is 1,244 kilojoules. So this represents the energy that has to be put into the reactants in order to change them into products. So in a few minutes we'll take a look at what an exothermic reaction looks like. But this is a useful way to understand and summarize what's going on in a reaction. I've written out the reaction for the combustion of methane, CH4, and if we go through the process and make the calculation using bonds broken versus bonds formed, in this case we find that delta H is going to be minus 890 kilojoules. So that means that you are getting more energy released when you're forming the reactants than is being taken in when you break the bonds for the reactants. So this kind of reaction we refer to as exothermic. And if we were putting the energy term into this reaction, since the energy is being produced, we would put on this side, now this is what's a little confusing, so this means that this much energy is being released. So when energy is released, it's a product, and when energy is being absorbed, it's a reactant. So it's always going to be positive in the equation. But the delta H value is going to be either positive or negative depending on whether energy is absorbed or it's released. So, and just like in the previous example, if we made a little graph of this situation, this one would look like this. And the minus 890, or the 890, is the difference between these two. So this represents 890 kilojoules. So if we take the difference between the energy of the products over here and the reactants, then that difference is going to be 890, and because the products are lower in energy, it's going to be minus 890. So you should familiarize yourself with these two graphs and these terms and how they're put into the equations, and the OWL exercises 8.4 will give you some practice in doing that.